Good afternoon. Welcome to episode number 30 of the ZOOMTOWN experiment. Now, I must start off right away with an embarrassing admission. Somewhere along the way in code development and starting the presentation of these stories, I got my code mixed up. So some of the previous code you've been looking at is perhaps errant. It's been working so far for what I've presented, but as I discovered today, my code for the line following was my very first stab at it that was not working very well. I started filming the story and I'm explaining to you the code and I'm thinking, this doesn't seem right. After a while, we figured it out, and so what I had to do, I couldn't find my more current code for it, so I had to code something together real quick for the line following. I apologize for that. It's just been one of them months, I guess. What we're going to cover is line following, of course, today, and just to recap, last week we covered encoder steering. Line following is nearly identical. Even the rules that I'll quickly go over again are nearly identical except for one. So let's start with the rules, and then from that we can build everything else up for this story. Rule number one, if both wheels are the same size and both wheels are rotating at the same speed, the Zoomie will move in a straight line. Just as before, nothing changes there. That aspect is the same. Rule number two, the Zoomie's heading will be equivalent to the line with minimal deviation. Now, if you remember, with the encoder steering, whatever heading the Zoomie was pointed at, it would just take off from that and head in that direction, hopefully in a near perfect straight line. Well, with line following, the heading, regardless, within reason, of where we start, the Zoomie should, pick up that line and follow it along its heading. And that is the big difference between the two. Now, for our purposes here in the ZOOMTOWN experiment, our line following is going to be mostly restricted for straight line travel. For corners, we're going to try to handle that a little differently. Rule number three, everything imaginable will work against rules number 1 and 2. And isn't that always the case? That good old Murphy's Law problem. Anything that can go wrong will go wrong. Rule number 4, adjustments must be made to the velocity of each motor as frequently as possible. And just like the encoder steering, we've got to do it as frequently as possible, and we're going to do that from our deterministic loop running at 5 milliseconds. Rule number 5, the adjustments being made have to be at a rate greater than the errors experienced, or the error magnitude will continually increase. Now, in the case of what we're doing, you're going to see that our error rate value is extremely high compared to the feed rate or the velocity inches per second. We'll learn more about that in code. Rule number 6, if the unit of error is not equal to the unit of adjustment, a ratio or proportional calculation is needed. Well, as I just mentioned, the difference between our error and our adjustment value is very, very different. And that's going to make it a little bit more challenging to tune this. Now, this will be a PID control loop. I'm hoping to stick with just the proportional component of it. If I've got to add integral and derivative, it adds cycle time, and I'm trying my best to avoid that. Now, before we even start looking at the code, let's just watch the Zoomie run. Right now, I have not tuned the PID, but it gives us a great starting point. We're going to explore that together and tune it up so that it runs a lot better. So let's get a start point on this. That looks like the old dance we used to call the shimmy. Yeah, that's a little bit on the nervous side. And let's see if PID, or the proportional component of it, can help us tone that down. But the one thing I do in tuning PID algorithms is I want to take and analyze the data more than just watching it in motion. It tells me more of a story, and you'll see what I mean here. I do this with spreadsheets, and I believe I've done previous stories showing something similar. So what I'm going to do is copy this data here that is printing out the error of both the left and the right sensor. And that's a deviation amount from where I want it to be, or the target, or theoretically the center of the line that it's following. So I'm going to copy that. I'm going to paste that. If you use Paste Special, usually it gives you an import dialog box, and it's going to separate the two columns of data that we're outputting. The left sensor and the left sensor and the right sensor data. And we've got that there. I'm going to highlight those two, select graph, and I want a line graph. Those area graphs don't really help tell the story. And wow, doesn't that look just like the motion we saw? Really nervous, really jittery. What we would like to have there is a much flatter line. Now, we're always probably going to start not perfectly on the center of the line. So we'll see a spike there, and then it should hopefully narrow in very quickly to just traveling in a straight line. And this is what we're going to work towards as we move through this whole tuning process. I'm going to use the spreadsheet, graph the data, see if that matches what I'm seeing with my eyes and movement, or if I see any other subtle points of interest that would take me on another path. Let's dive into the code. We're going to scroll down and get to our velocity control area right here. This is where we were working, of course, with the encoder steering. Now, the one that runs all the time is not set velocity, auto adjust velocity. This runs every 5 milliseconds in our deterministic loop. And that works very well for doing PID control and other forms of control. I want to get down to this area of the code, and this is the area right here. Let me try to make that a little bigger. We'll make the files go away. And hopefully that's plenty visible for you guys. This is the area code that I just changed. It's dramatically different than what was there in the previous versions. Now, I don't know yet if each Zoomie will have to individually be tuned. If that's the case, I have that Z profile file where I can put unique information for the Zoomie and load that in. And then that way I won't have to alter the source code. I can import data that is specific to the Zoomie running within a common program. And these here, this on center and this p-value for proportional, these two may have to go into that file as they may need to be tuned for each particular Zoomie. I won't know until I get them all built and start seeing how they behave. But as we look through the code here, we're in line following mode. I've got a variable called on center 49,500. That is the reading of each of the two sensors when it is pretty close to centered over the line we're following. The p-value is our proportional. You notice that that is a very small number. It's below zero. It's a thousandths, 0.001. And that is because we're looking at numbers that are very large from the sensor, but our feed rate, our velocity that we're adjusting is a very small number. Here we're looking at 49,500, whereas our velocity is somewhere between 1 and 9. So by multiplying this, or our error, which will be in this neighborhood, times this, we can reduce it proportionally so that we can affect the feed rate more directly to what we need. So now I'm going to move through the code here. I've got L error and R error. This is calculated by taking that amount, which would be ideally on center, and I subtract that from the sensor readings. That'll tell me how far I'm off on each side. Of course, one should be, well, mathematically, one would be negative, one would be positive, but they should always be pretty much equal. I'm going to calculate an amount that I'm calling the shift amount. This is the shift amount to get to center. And that is calculated by taking the left error minus the right error. And then I'm going to take that amount and multiply it times our proportional. And that is this value here. As mentioned, this will be a fairly large number, and we need to reduce its size. And for one wheel, we need to go faster. The other wheel will go slower, and that will create a sort of pivot turn. Essentially, what that's going to boil down to, instead of going, so to speak, a lot faster on one wheel, I can go halfway faster on one wheel, halfway slower on the other wheel in this calculated adjustment, and that way I can get a more efficient process for getting the steering to react more quickly. So in other words, one wheel speeds up, one wheel slows down, and it's going to make a turn, a tighter turn than if just one wheel was doing that steering. We're going to preset our left and right run velocities based on our singular run velocity. And from that, we're going to add in our shifted velocity, our proportional control or adjustment for velocity to cause the steering. Finally, I print out this left error and right error, which is what we're really trying to get rid of or minimize, and that's what we're trying to graph. So we found that at 0.001, it was really nervous, really jittery, so it's way too aggressive of a value. Now, if you've done a lot of PID tuning, realistically, you're almost working in a range of around a whole number of 1 or something like that, or 0 to 1. So this is really on the extreme opposite end of the scale. But I'm going to add another 0 to here. I'm going to drop that down by a factor of 10, and we'll see if it behaves any differently. So we'll watch this one run, and then I'll go ahead and graph that. Wow, I think that looked really good. Let's see what the data tells us. Okay, here's our before. This is what we had on our previous run. Now I'm just going to paste the data in here and see how our graph changes. That is much better. Now before we had much higher outside values, and right now we'll see we're peaking out at about 5,000 there, about the same thing, about 5,000 on either side, and that's our first movement. It's going to find its way, and then you'll see this. And for the most part, it's actually staying within a pretty reasonable range. Now again, these numbers seem really dramatic, right? 4,000. Well, to give you a perspective, the number, if that value is 35,000, that equates to approximately 6 millimeters or about 1/4 of an inch. So when you get down into this range where we're at here, we're in about a, well, actually if we go side to side, we're in about a 3,000 to 4,000 range. So this isn't, it looks really bad here on the graph, but in reality, dimensionally, we're really close. So what I'm going to do, I will go ahead and I'll make a number of experiments. We'll keep adjusting that proportional value to see if I can make improvements here. I won't bore you with all the details. We'll just quickly review the result of each of the runs and the proportional value. Now, because this worked out so close at the 0.0001 value, I actually think that's going to be a really good baseline. But I thought, let's go one more factor of 10 greater on the proportional, and we'll see how it behaves over on the test track Z. Now you see it trying to wander around aimlessly. That's too passive. We need a much more aggressive approach. But let's look at the data. And that looks a lot like what we watched happen while it was moving along the course. Now we're back up into some pretty high numbers again, 15,000, about 18,000 here, and it never really corrects. It's just wandering too far into this direction, then it starts the course correction, and it's so slow that it can't get caught up. When it starts changing, it goes too far. It's just taking too long to do anything. So I'm going to go back to that 0.0001 value and then tweak up or down from there. I will also be repeating this process over and over a number of times, and if I find anything interesting, I'll show you the effects of what I found there. Otherwise, once I get it down to a point where I find it reasonable and acceptable, I'll lock it in and we'll wrap up the discussion at that point. Well, as you saw, we ran a number of tests, and I've gone through, you probably won't be able to see this, but these are the different proportion settings that I've set to. We had our baseline, which was 0.0001, and that looked like that. Then I increased it to 0.00012, and the tail end got a little tighter. Then to 0.00013, kind of got better, but I saw kind of a weird bumpy in here, and that's always overshoot. Then I got to 14.00014, and it actually looked pretty good. Now in scale, again, that's 2,000 here. That's a very tiny amount physically in the dimensional world. When I moved on to 0.0015 all the way up through 0.0020, it kind of got worse. You'll see this area get worse and worse and worse. So then I went back to my 0.0014, and that looked pretty good all the way across. Now I don't expect these numbers to be perfectly centrally located around 0, because you'll notice that my lines on the layout, I use a two-tone system. I've got a white line down what ideally should be the center line of a light gray wider line. And if you look at it closely, and you can see it, you should be able to see it on your screen. See the area where I've got this Well, look in this area here. Notice how narrow the gray line is there and how wide it is on this side. I'm not a very good line artist, so I didn't do a good job painting that. And that's why we see this fading away at the end on the graph. Now, for one last test on this, I should go back to the code, show you that nothing crazy went on there. Here's our P with the 0.0014. And all the rest of the code in that area is exactly as it is. But just for one last test, I thought we would see how it does going around a corner, even though that's really not its intended purpose, but it should prove whether or not the line following is working pretty good. I'm okay with that. Not so bad. Well, hopefully you've got an idea, a little better idea of dealing with a very simple PID control routine and line following, and using a spreadsheet to help tune it is really a great practice in my opinion, because we can look at numerical data, but it's hard to figure out what's really going on. We can observe it with our eye, but like that initial high impact movement that we see, well, okay, we can't really see how much that was, and that's where graphing it can really help reveal what's really going on. Now, in all reality, this is probably going to be tuned again and again over the course of the upcoming episodes. If I run across anything that was pretty drastic change, of course, we'll revisit it. But for right now, I think I'm comfortable with that line following doing exactly what I want it to do. So that'll wrap up this episode. Next week, I believe we're either looking at the Hall effect sensors or the collision avoidance system. One or the other's coming up real soon. I look forward to seeing you then. Thanks for watching.